Good morning.
Morning. Yeah.
Good morning.
Good morning. Yep.
Good morning.
Good morning, sir. Okay. Okay, girls. Any questions? Any questions at this moment? Or anybody want to say something? No. Okay, go. So we, yes, okay. Still, we'll just okay. Continue on with chapter number 2. Now, what we said yesterday was just a brief review. That for sound, well, okay. First of all, is okay. Sound was a form of energy. Travels in form of waves, which is going to be as okay a longitudinal wave. Why was it a longitudinal wave? Because if the particles moves back and forth like this, the wave will either be traveling in this direction or in this direction. Yeah. Another thing that we could say was that okay, yes, it was also a mechanical wave. And why was it a mechanical wave? It's okay because it travels due to motion of particles in the medium. Now, for sound to be produced and for sound to travel, we needed two things. We needed, yes, okay, what we will call a source. So you can say, okay, a source of sound. Okay. So any sound that is produced, that's mainly because there is something or some source that actually is going to be producing it. So for us, yes, okay, the source of sound is going to be the transducer. Or we also, yes, okay, from time to time, we refer to as the probe. Here. Now, how it produces the sound, we're going to just, okay, talk about that in chapter number 8. But for now, just remember this matter, okay, the source of our sound is going to be the transducer. Now for the media, that's okay, for the sound to be able to travel. Yes, okay, we will need a medium. And as far as we are concerned, yes, okay, the medium here is going to be the tissues. Okay. Very medical says, okay, as far as the nature of tissues was concerned, there were mainly, yes, okay, three types. We had tissues which are going to be solid. There are going to be tissues which will be liquid. And we have medium, which will be gases, or we can say, yes, okay, here. Okay. Sound is going to, yes, okay, travel through each of these, but the only thing that is going to be, yes, okay, different is fastest, slowest, and we can mean this as okay at an intermediate speed. Did that make sense? Clear? Okay. Now, how was it that sound traveled as a wave? Was mainly as okay by, as okay, compression. And we can say as okay, do this way. Rarefied particles. Yeah, where it mainly meant, yes, okay, when particles were compressed, the phase of compression, that they were close to one another. Whereas being rarefied was far away from one another. Okay. But it's okay, they are going to be moving back and forth. Back and forth. And likewise here, it's okay, they will be moving. We can say it's okay, back and forth. Whereas maybe it's okay going to be during compression, that there's going to be, we can say it's okay, max transfer of energy from particle to particle. Okay. Did you get that? Any questions about this? Now we had a source. And you can see it's okay, we have tissues. Now this source here is okay, that is going to, is okay, produce sound. And we can mean says okay, that sound is just okay, going to just okay, travel through the tissues. Now goes there's something here that we call, yes, okay, the acoustic propagation. Oops, sorry. Properties. Now, some of you will say, what the blue is acoustic. Now goes acoustic, that is mainly it's okay, just a fancy word for sound. Clear? Or we can say it's okay pertaining to sound because it's tick, right? Okay. So acoustic is mainly as okay going to be as okay. Something is okay related or pertaining to sound. Mainly because where acoustics means sound. Propagation. Now we can mainly say as okay, coming from receding or moving ahead or progressing. Clear? And properties are properties. Now, what acoustic propagation properties is going to be, that's mainly as okay, we can say as okay, that will be the effect of the medium upon the sound wave. So what is going to happen is that as the sound travels, and yes, okay, it crosses through different mediums, that the medium is mainly as okay going to affect some of the parameters of the sound wave. And so any effect that the medium has on the sound wave as it travels through the tissues, in this case, are the medium, that is going to be referred to as an acoustic propagation property. Clear? We will briefly, yes, okay, mention these or get introduced to that in chapter 3. But the actual details of acoustic propagation properties is going to, yes, okay, be discussed in chapter 6. Clear? Okay. One common example, and pretty much okay, as one of the, we can say that the major example of an acoustic propagation property is what would be attenuation. Attenuation is nothing but it's mainly as okay, just an example of an acoustic propagation property. As the sound travel, yes, okay, sometimes okay, the sound wave is going to attenuate. Now, what that attenuation will be, yes, okay, we'll talk in details about that when we get to that point. Okay, guys. So for now, just remember, as sound travels through any medium, the effect that the medium has upon the sound wave. So that's going to mean yes, okay, be changes in the sound wave characteristics. That is going to be called the acoustic propagation properties. Is everybody clear upon that?
So the acoustic propagation, is that like, that would be the Doppler, right? That would be the source, or
No, my dear. Acoustic is just a fancy word for sound.
Okay,
Clear?
yeah,
Propagation is mainly as okay, we can say as okay, just pertaining to as okay, progressing. Clear? And properties are properties. They just label it this, okay? We can mean it as okay, what are going to as okay be the properties of the sound, or what's going to as okay be the properties of the sound as it progresses. Because you can mainly say as okay that here, sound was produced by the source, right?
yeah,
Clear? And what I mainly as okay just said that okay, yes, it travels through different tissues. So it's mainly as okay, just propagating in this direction here. Okay, now what an acoustic propagation property actually is going to be is that if you compare the sound here to what we have here, it will have changed. And those changes are going to be as okay, mainly what we call as okay, acoustic propagation properties. Because, okay, but what was it that caused these changes in the sound? It is actually as okay, going to as okay, be the medium that affects certain parameters or characteristics of the sound wave, okay, to cause them to change. So that will be as okay, what we call an acoustic propagation property. Okay. A solid example of that is going to be as okay attenuation, which we will as okay discuss in detail in chapter 6. I can just give you an example. Okay. Now let's say that okay, yes, I'm standing in the parking lot by the school and talking. Now the people who are standing close by will be able to clearly hear what I'm saying. People who may be standing as okay by the gas station will have a problem hearing what I'm saying. Not to talk about as okay the people who stand down by as okay the highway, the 95 will have they're probably not going to be able to hear me. Why? Mainly because as okay, the sound will attenuate by the time it reaches to the highway. Why? Mainly because as okay, me standing here in the parking lot talking. As okay, what it is I'm producing sound. And we can mainly say, okay, the farther and farther and farther it travels, the more is it that it will attenuate. So here, yes, okay, we can mainly say, okay, that the sound does not reach this far. Why? Because, okay, as it traveled, whether it's air, whether it's buildings, whether it's whatsoever that comes in the way, is going to be medium, which is going to, okay, affect the sound as it travels. Did that make sense?
yes,
If that was not the case, then okay, yes, you will be able to hear what a guy is sitting at the other end of the globe. Let's say it's okay, Japan was doing or talking about. Well, you can now, but that's mainly because okay, that's okay, the sound can travel, that's okay as electric signals and so on, so via cables or via okay, internet signals. But that's okay. If not for that, that's okay, that's okay. The sound would, yes, okay, change. Or we can say, okay, certain characteristics of the sound wave will change as it progresses. What causes it to change is mainly as okay, going to be the medium that it travels to that will cause those changes. That's going to be as okay, we can say it's okay, the effect that the medium has upon the sound wave. as the sound wave travels through the medium are going to be referred to as acoustic propagation properties. So that's okay. A solid example for that is attenuation, which we'll come across in chapter number 6. Any questions, girls? Now, girls, it's not a one-way traffic. If the medium can affect the sound, the sound wave can also, that's okay, affect the medium. Okay, and that is going to be, that's okay, what we can call, that's okay, biologic effects. These biologic effects here can also be referred to as bioeffects. So what is going to be bioeffect or biologic effect? It's just going to be, you can say, it's okay, the opposite of an acoustic propagation property, which mainly then will mean that, okay, that's going to be, as okay, the effect of the sound wave upon the medium. Now, what would that mean? That would mainly, as okay, mean that, okay, as the sound wave, yes, okay, travels through the medium. Clear? Now, just keep in mind, go that, okay, a sound wave, what was it? It was a form of energy. Clear? Now, what mainly, yes, okay, will happen is that, okay, yes, as it travels, yes, okay, through the medium, some of the energy actually, yes, okay, will leave the sound wave. And mainly, yes, okay, what we, yes, okay, would say is get picked up by the tissues or absorbed by the tissues. Okay. And that is mainly, that's okay. So mainly, that's okay, energy absorbed by the medium. So, that was right. As the sound travels through it, is going to mainly lead to, as okay, what we can call bioeffects or biologic effects. Okay. Now, although it's okay, here was sound energy, but what I said yesterday is that, okay, as energy has a characteristic that it's able to, yes, okay, change its form. So sound wave that is going to, yes, okay, sound energy that is going to, yes, okay, be absorbed by the medium as the sound travels through it. That is mean it's okay, going to change into heat energy. And that heat energy is okay in large amounts, actually is okay, can affect the medium or the tissues. So that's what we will call is okay, biologic effect or bioeffects. The details about that is going to be as okay, chapter number 24. which is a little bit disappointing. Okay, because girls, ultrasound is a low energy test. It's not that we are transmitting as okay huge amounts of energy into the patient. Okay, compared to other yes okay, we can say it's okay diagnostic imaging tests. X-rays, for instance, CAT scans, that's large amounts of energy. Not just large amount of energy is going to yes okay be radiations. So is an okay as an MRI. Large amount of okay as magnetic energy. Okay, so when you talk about as okay, those as okay diagnostic imaging modalities as okay, bioeffect is a lot, it's a big thing, it's a huge thing. In ultrasound mainly as okay, because it is still being as okay studied so far as okay, it really hasn't shown to as okay cause any bioeffects or biologic effects. And that's why as okay, it's also as okay a relatively as okay safe way of okay as doing as okay diagnostic imaging compared to CAT scans, X-rays, MRIs, etc., etc. Because they have huge bio or biologic effects. Whereas okay can lead to as okay, you can say it's okay damage of the tissue. Okay, irradiation may be as okay go as extreme as actually as okay actually causing if not death of tissue or tissues, causing changes that actually is okay can trigger cancers. Is that clear? Okay. So yes, okay, for X-ray, that's like for ultrasound. That's okay. Theoretically, yes, okay, we can say it's okay that there may be bioeffects or biologic effects. But practically, well, okay, it's still being studied. So far, yes, okay, ultrasound is yes, okay, considered to be as okay, yeah, relatively as okay safe type of okay diagnostic imaging, especially as okay in relation to bioeffects. Yeah. Acoustic propagation properties. What is the effect that the sound, or sorry, the medium has upon the sound wave as it travels through? That's what you call an acoustic propagation property. Biologic effect or bioeffect is just opposite. What's the effect that the sound wave or sound has upon the tissues or the medium? Clear? Okay. So mainly as okay, just to understand that, just keep in mind that okay, yes, sound is a form of energy. Clear? Okay. So yes, okay, as energy travels, yes, okay, it will decrease. It will decrease. Clear? What is going to cause that decrease? Mainly as okay, the kind of medium that it's going to interact with. So that decrease in the sound waves energy is going to be as okay an acoustic propagation property. The best example, and pretty much okay, the only example that we were talking about primarily is attenuation. Clear? Okay. Another way, what is going to be as okay the effect that the sound, which is an energy, has upon the medium. That will be a biologic effect or bioeffect. What is going to cause that? Well, okay, as sound travels through a medium, the medium will okay absorb some of the energy from the sound wave. Clear? Okay. And you can mainly say, okay, the more energy that, okay, as a tissue or a medium absorbs from a sound wave, well, okay, the more likely is it that, okay, as that sound energy is not going to be sitting there in the tissues and singing Christmas carols or happy birthday or something. It's going to be converted into another form of energy, which in this case here is, okay, will be heat energy, or what we as, okay, in scientific terms will call thermal energy. Did that make sense? Okay. So that's okay. That will be as, okay, what we call the acoustic, biologic effects. Any questions about these two? So did I make myself clear on these?
Yes.
Yes.
Good. That's all I need to know. Okay, goals. Now let's just go then on to, yes, okay, what we will call, yes, okay, the acoustic variables. And again, yes, okay, as I just said, what the blue was acoustic, we can make, yes, okay, just say, yes, okay, a fancy word that means sound. Yep. Okay. Now, if you look in your book, yes, okay, the very first sentence says that sound waves are identified by, now here we just want to, okay, do this. Oscillations of, that's okay, what we call acoustic variables. Okay. Please underline, highlight, whatever you want to do. Clear? Now the question may just then arise, okay, what the is oscillations? Now go oscillation, that's mainly as okay, just going to be as okay, we can say varying distance between particles. Which particles? The particles that mainly as okay causes the, or the particles that moves, which causes that's okay the sound wave to travel. Now goes when we talk of the acoustic variables. because that's going to be as okay, 3 acoustic variables. The 3 acoustic variables are going to be, first of all, will be pressure. The second acoustic variable will be density. And our third acoustic variable is going to be distance. Clear? Now go, yes, okay, here this distance could help me, yes, okay, a little bit more, yes, okay, specify because I mean, yes, okay, we can say we're going to be distance of particle motion. Clear? Now girls, it's going to be, yes, okay, a must for you girls to remember, yes, okay, what the acoustic variables are going to be. So it's going to be pressure, it's going to be density, and it's going to be distance. Whereas, okay, here when we say distance, it actually means just, okay, distance of, or distance of particle motion. Is that clear? So if you have been asked what are the acoustic variables, pressure, density, and particles or distance. Did you girls get that?
Yes.
Good. Okay, let's talk business. Now, primarily as okay, what we can say as okay, the unit for pressure is going to be Pascal, abbreviated by PE. Now, some people may say, yes, okay, what the blue is a Pascal. Now, if you yes, okay, mean yes, okay, just define pressure. That's going to say, okay, give us a little bit more, yes, okay, clear idea of what the blue is, okay, a Pascal is going to be, or what pressure is. So pressure is going to be, yes, okay, the concentration of force per area. Clear? So if you look at this, the unit for force is going to be Newton. And the unit for area is what? What's the unit for area?
Is it the capital A?
No.
No.
What is the unit for area?
Is that any distance times 2?
Exactly, very good, exactly. So any unit of distance, squared, right? Okay, please, Nicole, please don't say times 2 because, so we can say it's okay, meter square. Did that make sense? So we can
Yes.
actually say, okay, a Pascal is going to be as okay, or we can say 1 Pascal maybe is okay. 1 Newton per 1 meter square. So force is force. The unit for force is Newton. Okay, why did they call it, why did they label, yes, okay, the unit for force as a Newton? Because he was the guy who actually, yes, okay, came up with the whole idea of, okay, as force of gravity. Actually, yes, okay, calculated the force of gravity. Distributed in an area. The area was going to be as, okay, any unit of distance squared. Okay. And Nicole, it was good that you gave the answer, but please do not say it's okay. That's going to multiply by 2. Because that's okay. If we have, that's okay, let's say it's okay, 4 meter square. If you say, okay, as 4 multiplied by 2, what you get as area is going to be 8 square meters. That would be wrong. It's going to be 4 multiplied by 4, which becomes 16. So that will be the area. Clear? So yes, okay, squaring it is mainly going to mean that, okay, you multiply this number here by itself. Okay, dear? Nicole, did you get that, my dear?
Yes. And
Okay.
what about the number 3 on the top? That's cubic.
If it said,
right?
if it had been, okay. If you said, okay, that's going to be as, okay, volume, you know, you can say it's okay, or 3,
Well,
then
how
it's
you
okay.
call that?
Then you just go this, then it's going to be 4 times 4 is 16 times 4 is 52.
But how you call the number 3? That's cubic, right?
That's going to be a cube. This is
Cube.
going to be square.
Okay, got it.
Okay, so raised to the power 2, let's say it's okay, anything raised to the power 2, that is going to be square. Clear? Anything is okay raised to the power 3 is going to be cube or cubic. Capiche?
Got it, thank you.
Good. Okay, goes. So we can say it's okay, that was mainly as okay, your definition of pressure. Concentration of force per area. Now, if you guys think that this is all you need to know, then you are wrong. Because the next thing comes. What is the relationship between pressure and force? What is going to, yes, okay, be the relationship between pressure and area? Now, girl, usually it's okay when we do a relationship like this. We mean it's okay, we'll say it's okay, pressure, what was the formula for it? It was force divided by area. Now, if we say that we, yes, okay, want to establish the relationship between pressure and force, That's when we mainly it's okay, then we'll say it's okay that area is constant. And what we mean to be constant, that we don't change it. He says, okay, it's going to be the same area, but we're just going to just, okay, change the force and see how that affects the, and how that's going to just, okay, affect the pressure. Okay. But what we mainly as okay can say or will be end up saying is that pressure that is going to be as okay directly proportional to force if area is constant. What would that mean? That would mainly mean that, okay, yes, if we increase the force, there would be an increase in pressure. If on the other hand, it's okay, if we decrease the force, there will be a decrease in pressure. So pressure and force are directly proportional. Or you can mainly, as okay, just establish that from the formula. Because pressure was equal to force over area. Now let us just take an example of how that makes sense. Let's say that, okay, as we have an area here. This is an area. Yeah. Let's say that, okay, as this area here is 2 square meters. Right? Okay. And okay, yes, that's for another example. Yes, okay, we have, okay, as another area as well. And there's also going to be, it's okay, 2 square meters. So here what we did was, okay, yes, we kept the area constant. Yeah. Okay, we have 2 examples of, okay, yes, where we kept the area constant. Is that clear? Now, in one case, that's okay. What we will do here is we will apply as okay a great force. Let's say it's okay that we apply a force of 20 newtons. So that's going to be as okay a great force, right? There's okay, and the other area, which is still the same, if the area is still the same, we apply a lesser force. Let's say it's okay, we apply a force of just 10 newtons. What we mainly as okay want to do in these cases here is okay, as mainly as okay, what the hell? Calculate our pressure. Because the pressure is mainly going to be as okay, how much force is it that is going to just okay be distributed in this area here and this area here. So for example, A, for instance, we can just say it's okay, this is A, this is B. For example, A, our formula is going to become 20. And we can just say it's okay, 20 newtons divided by, okay, the constant area, which is going to be, it's okay, 2 meters squares. Now, if you just do the math, so what did we end up as a force or having as a force or pressure, sorry, is going to be as okay, 20 newtons per square meter. Which is going to be as okay, sorry, it's going to be as okay, the great force. Oh, shit. Okay. Where if you go to yes, okay, example B. And yes, okay, now I want to yes, okay, calculate the force or pressure. It's going to be yes, okay, the low amount. We can say, okay, 10 newtons per same area, 2 meters square. And when we just do the math here and check, what do we end up with? A pressure of 5 newtons per meter square. Yeah, okay, now we can say, okay, this is a lower pressure. And this would be a greater pressure. Did that make sense? So pressure is going to be, yes, okay, directly proportional to force, or force is directly proportional to pressure. Clear, provided that, okay, yes. For this here is okay, we kept the area constant. Meaning it's okay just to establish it's okay what the actual relationship between pressure and force was. Is there anybody who has any doubts?
I do.
Okay, what's your doubt?
Can you go over another, like, because I understand that how pressure is directly related to the force,
Mhm.
and it's only because when the air is constant. But
Yeah,
I think I got lost when we're trying to find like the Newton and the I guess.
Newton is just the unit for force, my dear.
So we're just trying to find the force and the pressure.
We're just establishing is okay what the relationship between the force and pressure was. I already said that okay, as they are directly related. Well, I demonstrated it with okay as an example. There, okay, as we have the same area, 2 square meters, right?
Yes.
On 1K and one place as okay, we apply a force of 20 newtons on that 2 meter square area. Whereas on the other case, as okay, we apply only a 10 Newton force on that 2 square meters.
Okay, now I get it, because those both was just examples
Exactly.
of the forces.
So here, yes, okay, example A, that was made, okay, that was a great force. So we end up with a greater pressure because it comes out to 10 newtons per meter square, right?
Okay.
Where, okay, for the blue, it was not 10 newtons, but when we put it into the equation and did the math, we end up with, okay, as just 5 newtons, a pressure of 5 newtons per square meter. Because it's okay, applied as lesser force. So that's how we mainly hence can say that, okay, as hence proved,
Okay.
or based on this, that pressure is directly proportional to force. The greater the force, the greater the pressure. The lesser the force, the lesser the pressure.
So because we already know it's directly related to each other, the pressure and the force, we're just looking for it to find out what is the force.
Yeah.
Okay.
But you then also have to, yes, okay, look at the area, right? Okay. Now here we kept the area constant mainly as okay, because what we just wanted to establish was what is the actual relationship between pressure and force. So you say, okay, to determine that relationship, we need to keep the area constant. Clear? If I change the area and say, well, okay, here is going to be 10 newtons. Okay. Or we can say, okay, 20 newtons on a 20 square meter. Then that's going to be as okay. In this case, yes, okay, then you will have a lesser pressure than you have over here. Because when you do the math here, then it becomes 20, which is your force. Then, okay, it's divided by 20. Which now is, okay, your new area. And what it becomes your force or pressure? It becomes just, okay, 1 Newton per meter square. But yes, okay, here your pressure, that's okay, became less because you actually also increased the area. Okay, so mainly that's okay, just to establish the whole pure relationship between force and pressure. We keep the third variable of the equation constant. Did that make sense?
Yes, and
Good.
we're always going to divide the force in the area.
Yeah, because that's the formula for pressure.
Okay.
That's the formula for pressure. There's no ifs and buts about that. This is the formula of how you calculate pressure. Because that is pretty much okay as what pressure is divided as, or defined as, is the concentration of force or area. Now, ladies usually is okay when a definition uses the word concentration of. It's always going to be as okay, a numerator divided by a denominator. It doesn't really matter. You can say it's okay, what is the definition of population in a city? For instance, you can mainly say it's okay, that's going to be the concentration of people or any area, for instance, if that's what you want to call it, right? Okay. We can say it's okay, square mile. Now, if for instance, okay, you said, okay, as what we found out from AKS doing a survey, accounting, or whatsoever, we found out that that was actually as okay, 20,000 people in an area of okay, as 10 square miles. You just calculate it. If you just say, okay, if that is the case, okay, but okay, the question arises, how many people do we have living in this city or town here per square mile? Because you did a survey for 10 square miles and found that there were 20,000 people. And you just do the math. So it's going to be as okay, 20,000 divided by 10. And you actually find that, okay, yes, per square mile. That is going to be as okay 2,000 people. And then they may say, okay, is it suitable? Do we say that, okay, this is a concentrated population, or is it a 10 populated area, or is it just a normal? That depends upon us, okay, how much. The statistic will say that, okay, as each person living in an area should be allowed to have at least this much area for him or herself. Did that make sense? So yes, okay, just keep in mind that, okay, as area is constant, if force increases, pressure will increase. If the area also changes, then okay, and that's going to have its own effect upon the pressure. Okay. But that's pretty much okay how you, yes, okay, will do the math. I'll do the calculations. So there is no doubt about, yes, okay, what pressure is. It's the concentration of force per area. Did that make sense? Okay. Any questions? Nope. Okay, goals. So we already, okay, established that pressure is directly proportional to force. Clear? Now comes the next relationship. Because we had something else in our equation, right? Which was, okay, yes, we will say, yes, okay, where is the relationship between pressure and area? And goes pressure and area is actually, it's okay, going to be, it's okay, what we'll call inversely proportional. Clear? So what would that mean? That if the area increases, the pressure will decrease. Right? And yes, okay, on the other hand, if the area decreases, the pressure will increase. And mainly because, yes, okay, goes since we has, okay, mainly, yes, okay, just want to, yes, okay, establish the pure relationship between pressure and area. That's why we mainly say that, okay, as we keep force constant. Now, as we just did with pressure and force, we can do the same with pressure and area. And we, yes, okay, mainly we say, okay, we'll have two areas where, okay, the amount of force is going to be the same. we can say as okay, 20 newtons. 20 newtons. Clear? But in one example, we can say as okay, we may have okay that 20 area as okay 20 newtons of force distributed over a greater area. Let's say as okay 10 meters square. Whereas for the other case, yes, okay, we will have it okay distributed over a lesser area. We can say it's okay. 5 meters square. Now we'll just label this one here as A. We label this one here as B. Now comes the thing. What's going to be as okay the pressure for A? That's where we have okay as 20 newtons of force distributed over yes, okay, a great area, which will be 10 meters square. Now, when you just do the math here, your force comes out, or your pressure comes out to 2 newtons per meter square. Whereas if you just do the same for yes, okay, B, where okay, well, the same amount of pressure, sorry, same amount of force. Now just apply the law as okay to a smaller area. What you get is 20 divided by 4 is, or 20 divided by 5 is 4. So you have okay as a pressure of 4 newtons per meter square. Where we mainly then can say is okay that this here, that's a greater pressure. Because we had a smaller area. Whereas this one here is a lower pressure. A lower pressure. Sorry. Mainly because okay, we had a greater area. And that mainly is okay, established the fact that pressure is inversely proportional to area. Because for a great area, we end up with a lower pressure. For a smaller area, we end up with a greater pressure. Any questions? Yes, girls. Any questions? Any doubts? That's what we call relationships. Yes, goes. Or we can mainly says, okay, whenever you have equations where a number is divided by a number. Okay, here it's okay, was pressure. Okay, it's always going to be directly proportional to the numerator. And it's always going to be inversely proportional to the denominator. Still lost? Mainly because we said pressure. That is what we are calculating. Here is okay, the force. That is the numerator. Area. That is the denominator. Well, what is it that you do? Whenever yes, okay, calculate this pressure here. What you mainly do and what the denominator mean is going to do is going to be the number by which you divide this. Or the numerator. So if that gets greater, this gets lesser. Or if this gets lesser, this gets greater. Now, please, that is provided that, okay, yes, this one here was constant. Now, if you keep the denominator constant, say, okay, this number here is going to be fixed, but we're going to change the numerator. If the numerator increases, that will increase the vector that we calculated. Whereas, okay, yes, if this decreases, then this will decrease. Because we are dividing it by, yes, okay, the same number. But if you just look back at the definition of pressure, or was it concentration of force in an area? Okay. Where force was the numerator. And area is, okay, in this case here is the denominator. So this is always going to be, yes, okay, so this fellow is always going to be directly proportional to the numerator and inversely proportional to the denominator. That's a common cheat that you can make. It's okay, apply to any case. It's okay where you have an equation where there's going to be a numerator and a denominator. Okay. So here we really can't just, okay, we can't change the definition of force. That's not of pressure, sorry. That's standard. So concentration of force per area. Now, the greater the force of this definition here is going to say, okay, put on your brain, the greater will be the pressure. Okay. Right, the equation is obvious from the formula, or from the definition, sorry. If you look at the definition, it's the concentration of. Once you see concentration of in the definition, you should already start thinking, okay, there's going to be a numerator and there's going to be a denominator. And good concentration should not be a new term. We talked about it in chapter 2 in bio and A&P. Right? Hypertonic, isotonic, hypertonic. What was that? The more salt or more sugar or more lemonade or more color or whatever you add to a substance is going to become more concentrated, right? So you can say, okay, a great concentration of lemonade per bottle of, well, okay, diluted lemonade juice. Because we added more lemonade extract or concentrate into it. Same volume, right? So a greater concentration. So you can say, okay, a greater pressure is going to be, it's okay, a greater concentration of force per area. And then vice versa. Whereas, okay, if we increase the area, if we increase the volume, and still add the same amount of, yes, okay, I have a lemonade juice, it's just, okay, a bigger container of fluid. Or, okay, apply the same amount of pressure, or force, sorry, onto the same area. That's going to be, it's okay, a lesser average force. Yeah. Any questions? Are you guys still lost in the relationships here?
No.
Okay. Is it clear?
Yes.
Okay. But Danielle, you can only speak for yourself right there?
Yes.
Okay. Okay. So should we go on to the next one? Okay. Good. And our next acoustic variable was what we call density. And again, goal, that's okay. First thing that we need to do is, yes, okay. We can say, yes, okay, define what in the blue is it that, sorry, a density is going to be. So density is going to be, and you see the same word here, it's okay. It's going to be, as okay, a concentration of. So what that mean, again, as we said, yes, okay, there's going to be, as okay, two things. One will be a numerator, one is going to be a denominator. Clear? And what the numerator is going to be and what the denominator is going to be, that is fixed. You can't flip around and say, oh, I want to put pressure by something else. Then that's not going to be density. That's going to be something else. You can make it up then in your own name. So here's okay, for density is going to be as okay, the concentration of mass per volume. And mainly as okay, as we look at this, that mainly as okay gives us the unit for concentration, or for density, sorry. Okay, which is mainly going to be nothing but, now the basic unit for mass is kilogram. But you can go gram, you can go milligram, you can go any, as long as it is okay as a multiple or a fraction of kilogram. Clear? Divided by volume. Now this volume could either, yes, okay, had been liter. It could be milliliter, it could be centiliter, or it could be, yes, okay, any unit of distance cubed. Right? Okay, so either you say it's okay, kilograms per liter or kilograms per, or grams per liter or whatsoever. It doesn't really matter. Okay, or you said kilograms per any unit of distance square cubed. Millimeter, centimeter, mile, whatever. Clear? Now the next thing would then be as okay, now what is going to be as okay, the relationship between density and mass and density and volume. So density equals, that is going to be as okay, directly proportional to mass. Which mainly will mean that okay, as if we increase the mass, that is going to is okay, increase the density. Whereas okay, as if we decrease the mass, is going to is okay, decrease the density. But please keep in mind here that that's provided that volume is kept constant. And we intentionally keep it constant in this case here because we made this okay, just want to just okay, establish the pure relationship between density and mass. What's going to be the effect of density if we increase the mass? What's going to be the effect of density if we decrease the mass? So it's establishing that pure relationship. That's why we kept the third variable here. It's okay, constant. Did you ladies get that? Now, mainly as okay, just to establish this, we can mainly as okay say, well, okay, as we have two volumes and we keep them constant. We say as okay, this is going to be as okay, two volumes, or let's say as okay, 2 liters. Clear? In one of them, yes, okay, we will yes, okay, apply yes, okay, great mass. We add okay, it's a great amount of mass. We can say as okay, 20 kg. Whereas okay, as for the other one, yes, okay, that's going to be yes, okay, a lesser amount of mass. Just 2 kg. Okay, so for one, yes, okay, we have okay, it's a great mass in the same volume. And the other one we have okay, it's a small amount of mass in the same volume. Now what we made is okay, just want to establish what is going to be as okay, the effect of mass on the density. And doing so, yes, okay, we will establish the pure relationship between mass and density. So yes, okay, it comes down to the same, just as we did for pressure. Then we can say, okay, in case A is okay, our density is mean it's okay, going to be the mass divided by the volume. Every mean is okay, just put in the numbers here. So that was 20 kgs or 2 liters. And when you do the math, 20 divided by 2 is 10. So our density in this case is okay, came out to 10 kgs per liter. Whereas if we do the very same as okay for B, the formula is the same, we just need to put in the values, which was going to be as okay, the 2 kgs or 2 liters. So what do we do? It cuts out, so our density in this case it becomes 1 kilogram per liter. But we mainly can say that okay, as here in the example A is okay. We had a greater mass, which gave us okay as a greater density compared to what we have over here, which was okay as since we have a lower mass, we will end up with a lower density. So that's how mainly as okay, the fact is established that, sorry, we can say okay, mass is inverted directly proportional to density, or it can be written out the other way around. Density is directly proportional to mass. Yeah. Because okay, if one increases, the other increases. If one decreases, the other decreases. Any questions? Is this part clear?
Yeah.
Okay. Good. Now we can just do the very same and say, yes, okay. We already established that, okay, yes. Density is directly proportional to mass, which mainly means increase, increase, decrease, decrease. Now we can just, okay, also, now just also just, okay, let's just establish, okay, as our relationship between density and volume. Now, if you just look at the formula for density, it was that mass divided by volume. So what do that establish? That mainly is, okay, establish the fact that, okay, yes, density is going to be inversely proportional to volume. Now, right, as, okay, as a physicist, how do we establish that? We mainly, yes, okay, we'll say, well, okay, we can take two constant masses, 20 kg and 20 kg. In one case, that's okay, we will distribute that. So let's say it's okay, a great volume. Let's say it's okay, 10 liters, for instance. Clear? On the other hand, we is okay, distribute that on a smaller volume. You can say it's okay. Four liters. Because it's okay, this will be as okay, density A that we calculate here, this will be as okay, density B. Now for A, as okay, we can say it's okay. What is going to be the density? It's going to be as okay, those 20 kilograms per 10 liters. Now, when we do the math, 10 divided by, or 20 divided by 10 becomes 2. So our density in this case as becomes 2 kilograms per liter. Whereas, okay, if we go on the other side and say of a B, the density, well, okay, the formula is the same, so we just put in the numbers. 20 kgs, which is the same as we had over here, but now it's okay, that's distributed on a smaller, okay, in a smaller volume, which is just 4 liters. Clear? Now, when we just do the math and say it's okay, 20 divided by 4 becomes 5. So our density becomes 5 kgs per liter. Did that make sense? So what do we have here? I think everybody can agree at, okay, yes. That 2 is a lesser number and 5 is a greater number. So, yeah. Right. We got that lesser number of density, mainly because we had a greater volume. And we got, okay, yes, a greater density because we had a lesser volume. So that means, yes, okay, establishes the fact that, okay, yes, density is inversely proportional to volume. Because the greater the volume, the lesser is our density. And vice versa. The lesser the volume, the greater is the density. Any questions? So we can mainly say, okay, the main takeaway from these things here is what you need to remember or what you need to understand. No. What is it that we mean by acoustic variables? What are the 3 acoustic variables? Now, what is the definition of each of the acoustic variable? What is the formula? Which is obvious from, yes, okay, the definition. What's the units? And what is the relation between, yes, okay, the acoustic variable, which was pressure, and density, to, yes, okay, to the 2 factors that makes up the variable. So for pressure, yes, okay, the 2 factors were pressure of force and area. You can't change around with that. That's fixed. Okay. Okay. So you can't say, well, like, I don't want it to be pressure by area. I want it to be pressure by force by something else. That's not going to be pressure then. It can become something else that you make up. And then you name it in your own name. Clear? Okay. So it's fixed. For pressure, it's force divided by area. Not volume, it's force divided by area. For density, it's mass by volume. You can't say what's going to be the difference if I put area instead of volume? Well, okay, then it's not going to be density. So simple as that. It may become something else, but it's not going to be density. Clear? Next is then going to be, okay, now what is the relationship between pressure and force? What is the relationship between pressure and area? Clear? What is the relationship between density and mass? What is the relationship between density and volume? Did you ladies get that? Clear? Now the last parameter is mainly as okay, just accounting for distance. And what I mainly said was distance. Okay, had I been writing this book as okay, I would be more specific. I said, okay, it's going to be accounting for the distance of particle motion. So all dependent upon is okay, how much a particle moves. That's going to be as okay, what will be the distance. Okay. And distance is going to be measured in okay as any unit of distance or length. So can somebody give me a unit of distance?
Feet.
Huh?
Mile,
Feet.
Feet, mile, okay. And
Centimeter.
centimeter, good. Now, how many millimeters do we have in a meter? Oops.
1,000. I can, hello? Can you hear me?
Yes, I can hear you.
Oh, I couldn't hear you. You said something?
No, I better be quiet.
Oh, so it's
It's not. Or was it? What was my question? Sorry. Okay, let me ask again. How many centimeters do we have in a meter?
100.
100, good. Okay. How many nanometers do we have in a meter?
A billion.
1 billion, right? Okay, good. Good. Okay, ladies. Okay. Now just take a short break. Okay. Don't just use your break, just okay, go out and okay, inhale all the carbon dioxide coming from Canada. Is it bad at your area too?
That's so funny. My son, when I was
Yeah.
with him yesterday, and he was like, "Mommy, why is it so smoky?"
Hmm.
I was like, "I don't know."
Yeah, I went by the school in the afternoon and it is, oh God, you don't want to get there. It's like, it's horrible. Like it's just like, okay, being in a sandstorm. That's how it looks. Okay. So, well, okay, just stay indoor and okay, yes. Inhale some fresh air indoors and okay, let's inhale some text from the book. Okay. And that's okay. And when we come back, well, okay, we're not going to just okay, going to just like a whole lot of details of just okay, the acoustic parameters, because we have a whole chapter. Chapter 3 is nothing but is going to be as okay, detailed account about the acoustic parameters. Okay, but we will go over those briefly, very briefly. Okay, and okay, and then what do we have next? Okay, yes, in phase, out phase, constructor and destructor interference and operators, then your chapter is over. Okay, so I see you ladies, should I say at 11:7, opposite of 7:11. Okay, so see you at 7:11. No. 11-7. Okay, girls. Okay, girls, welcome back. Okay. Any question, ladies? At this point, anything you want me to explain over again? Or you guys think you got a solid grasp on it right now? Yes, girls.
Sort of.
Palm it up.
So I have a sort of graph on it.
Okay. Where is giving you a hard time, dear?
With the pressure and area.
Okay, I told you. I mean, so okay, just make that okay as a common standard. We can say it's okay, you have any. It can be a variable. Okay. Which is mean is okay, going to be determined by two factors. Now, whenever is going to be that okay, as one factor is going to be as okay, numerator. And other is going to be as okay, a denominator. What we mainly can say is that okay, yes, the variable is always going to be directly proportional to the numerator. Okay. And it's always going to be inversely proportional to the denominator. Now, if you find the choke or variable here, and say that is pressure, over the numerator, was false. Here, what was your denominator? That was area. The same can we do as okay, we said density. Because the density is going to be okay, always directly proportional to the numerator, which in this case here was mass. Yeah, and likewise it's going to be as okay, inversely proportional to the denominator, which was volume. Did that make sense?
Yeah.
You can take another example and say, well, okay, yes. And say, okay, a variable is going to be as okay, pieces of chocolate each student will receive. Now, in this case here, we can say it's okay, our formula will mainly be as okay. This can be actually calculated by, we can say the denominator or the numerator is going to be pieces of chocolate in the bowl. Whereas, okay, the denominator is going to be the number of students. So it's the same. If we had, okay, as a less number of students and the same number of, okay, as obviously, let's do it this way. Number of chocolate pieces. For each student. Now, how do we calculate that? We can say it's okay, that's going to be calculated on using the formula that will be, or how many pieces of chocolate do we have in the bowl? And that's going to be divided by, okay, as we can see, the number of students. Now, if you keep the number of students constant, let's say it's okay, a dozen. And we is okay, increase the number, I have a great number of chocolates. Let's say it's okay, 240 pieces of chocolate. Is going to be distributed amongst 12 students. Then we mainly can say that, okay, as each student is going to just, okay, get a total of 20 pieces of chocolate per student. Whereas if you do the opposite and say, well, okay, we have a lesser number of pieces of chocolates. Let's say it's okay, that's just going to be another 24 pieces of chocolate. And the number of students is the same. What do you get? Yes, ladies. Each student will only get 2 pieces of chocolate. Right?
Yeah.
Good. Now, if you just keep the number of chocolates constant, pieces of chocolate constant, and say, well, okay, we have a total of 240 pieces of chocolate. Probably then it's okay, change the number of students. We can say it's okay to increase, we have okay as a great number of students. We can say it's okay, a total of 24 students. What is each student then going to get? He or she is going to get 10 pieces of chocolate. Right, okay. Whereas if you kept the same number of 224 pieces of chocolate, or 240 pieces of chocolate, but it's okay, only had 12 students, then each student would get 20 pieces. So here we can say that's okay. A lesser number of students will give each student, that's okay, more chocolate. Right, okay, as the pieces of chocolate was constant 240. Whereas if you increase the number of students, that's the problem. Then each student will get less pieces of chocolate. Mainly because our formula actually is okay, calculate how many pieces of chocolate we will give to each student was. How many pieces of chocolate do we have in the bowl? Distributed among how many students? So whenever you come across something like this, the variable, which means it's okay, calculate here, it's always going to be as okay, directly proportional to the numerator and inversely proportional to the denominator. So it was constant, it was the same. Whether we talked density. Okay. That density was always going to be as okay, directly proportional to its numerator, which was mass, but inversely proportional to the denominator, which was volume. But keep in mind, when we want to establish the relationship between mass and density, or we keep volume constant. Just to establish the relationship. Where if you say, okay, we want to establish as okay, a pure relationship between density and volume, we'll keep mass constant. Likewise, as we did for pressure. We said that pressure as okay was directly proportional to its numerator, which was force. But to establish that relationship, that's when we kept the area constant. Okay, there, okay, if you wanted to, yes, okay, establish the relationship between pressure and the denominator in the formula of pressure, which was area, we will keep the force constant. And that will give us, okay, the pure relationship between pressure and area, which was the denominator. So it's always going to be as okay, inversely proportional to the denominator. Because you actually, as okay, divide the constant factor here, which was force, by a bigger number. So if you divide as okay, the force by a bigger number, the pressure, the value of the pressure will be less. But if you divide the constant force by a smaller number, this number is constant. You divide it by a smaller number, it is okay. The variable becomes greater. So that mainly will mean that okay, as area and pressure were inversely proportional. Okay. Because when this increased, then pressure decreased. And vice versa. When area decreased, then pressure will increase. So whenever you have an equation of a variable factor, parameter, or whatever you want to call it, which is determined by us, okay, dividing a thing by a thing, it's always going to be, it's okay, directly proportional to the numerator, but inversely proportional to the denominator. That's what we call the relationship, right? Is there anybody who is still in doubt about, yes, okay, what it means to be directly proportional and inversely proportional? Everybody is good upon that, right? Clear? Okay. Yes, Dr. King, you clear?
Yes.
Okay. Good. Now, girls, the next thing will be acoustic parameters. And just like, yes, okay, there are 7 continents. Just like, okay, yes, there are 7 oceans. Just like, okay, yes, there are 7 levels of heaven and 7 levels of hell. And 7 days in a week. Likewise, okay, are there going to be, yes, okay, 7 acoustic parameters. Clear? Okay. And what these 7 acoustic parameters mainly is okay, are mainly is okay going to further do is describe the sound. All we can say is okay, the sound wave. Okay, goes. Now it's going to be as okay important for you girls to remember as okay, or know at least what are the 7 parameters. Now they're mainly going to be as okay, I will say as okay, first will be period. Then we will say frequency. Then we will say yes, okay, wavelength. And there's a reason I write them like this. Then we can go on to yes, okay, what we can call our intensity and amplitude. Oh, shit. And then at last we can say propagation speed. Okay. Now we mainly is okay going to talk the details of these in chapter number 3. Or we can say chapter 3 is pretty much okay as just a detailed account upon period, frequency, wavelength, power, intensity, and amplitude, propagation speed. The formulas, the definitions, the units, the typical values, and then the relationships to other acoustic parameters. To which are they related, to which are they not related. And it's okay, out of the 2 things, which is going to determine the period, the frequency, the wavelength, the power, intensity, and amplitude, and the propagation speed. And so on. So now goals, period. Now usually just okay, here in the United States, people say this is a period. That's not what you call a period, girls. This is what In English, it's called a full stop. I don't know why they started calling it period. That's a full stop. Period is going to be okay. We can say it's okay the time that it takes a sound wave to complete. So if we take a sound wave or one cycle, the time that it takes to complete, that time is going to be known as a period. So if it took this cycle here 1 second to complete, then it's okay. The sound here has a period of 1 second. Did that make sense? So the period is made as okay going to be how much time does it take for a sound wave to complete? We most likely as okay will have that's okay another sound wave. That may likely also is okay, maybe it's okay another sound wave. Like this. Okay. But for each of them, yes, okay, the period is going to mean that's okay, be the time that it takes each of these waves or cycles here to complete. Did that make sense? So if you guys remember, that's okay, or you may think, okay, where did they get the word period from? Now you may have to go back to your school days. Because, okay, you meet up in the morning and, okay, yes, usually people will say, it's okay. At school, you have a timetable, right? Okay. First period is English. Then, okay, a second period will be history. And third period will be math. Then you have lunch. Then you have, okay, the fourth period will be, as okay, you can say geography. And then your class is, school is dismissed. So why would I call it a period? Because it was going to be as okay, a certain amount of time for which as okay, you will be studying that respective subject during the day. Did that make sense?
Yeah.
Good. Anybody who didn't get it? Good. Now, girls. Second one is frequency. Now we can mainly say that, okay, yes, frequency. That's mean it's okay going to be as okay, we can say it's a number of cycles or sound waves in a unit of time. So what did I just do here? Okay, I said I made 3 cycles. Clear? We may say that, okay, as from here to here, this may represent, yes, okay, let's say 1 second. Okay, and in 1 second, what did we have? We had, okay, as a total number of cycles, which was 3. that will mainly mean that, okay, as our frequency, in this case, it will be, it's okay, 3 cycles per second. If this whole time span here was 1 second, and then 1 second, 1 cycle, 2 cycle, 3 cycle, dark green, light green, and blue were completed. Clear? That will mainly mean that, okay, in 1 second we have, it's okay, 3 cycles. So we can mainly say, okay, our frequency will be 3 cycles per second, or we could even say that this is going to become, or we'll say it's okay, a frequency of 3 hertz. Did that make sense? Probably not now, but okay, yes. Then we go wavelength. Now it's okay, just draw, it's okay, a cycle again. But if you just look at the word wavelength, this was one wave, right? And what does the word length is okay tell you? It's mean it's okay going to be the distance from here to here. That would be the length of the wave. Or we can say it's okay, the distance from the beginning of a wave or cycle to the end of a cycle or wave. This distance, that would be the wavelength. Now goes the reason that I wrote these 3 fellows here in dark green is because that these 3 fellows here is okay, they are all going to be related. But right now, I'm not going to be bugging you girls with the relationship of these. That's what we have chapter 3 for, okay? Okay. But it's okay, they are going to be related. Did you girls get that?
Can you please repeat the last one? Because I didn't get it.
Which last one?
I cannot read it anyway. So it's the third one.
Wavelength?
Yeah, that one.
Okay, it's the distance from the beginning of the cycle to the end of a cycle.
Thank you.
No problem. Mainly as okay. What do we do when we measure from here to here? The distance, the length, that will become the wavelength. When we measure it from here to here in terms of time, it becomes period. Okay, so that's okay. Power. Now power goes, that's me, that's okay, going to be, that's okay, the transfer. Or some people mean it says, okay, the rate of transfer of energy. That's what we will describe as power. But we can mainly say, okay, the power is mainly as okay, mainly going to be as okay. We can say as okay, physical measure of the amount of energy a sound wave will carry. Or it's going to be as okay, a measurement of how much energy is it that the sound wave has. That is going to be expressed as the power of that sound wave. Okay. Now goes intensity. That is an acoustic parameter. Density is an acoustic variable. Please do not mix up the two, because intensity is going to be mainly as okay, the concentration of what we have here, power over area.
Power over area?
Yes. Or the concentration of power per area. So what do you see here? We are again going to have okay, a similar relationship between intensity and power that we had in density and mass. And a similar relationship between intensity and area here that we had in density and power, density and pressure. No, sorry, density and volume. Or power and area. No, sorry, pressure and area, sorry. The amplitude goes is mainly as okay, going to be, we can say as okay, just describe as okay, how big. Or yes, okay, if you want to go another way and say that how small is it that the wave, or we can say okay, more accurately say it's okay, the sound wave is. Now you can mainly say it's okay, you may have, let's say it's okay, a big wave. Like this. This is going to be a big wave, or mainly you can say it's okay, this wave here is going to have a big amplitude or a great amplitude. Whereas, okay, you may also say, well, okay, we have a small wave. When, okay, when we say it's okay, it's a small wave, that's means it's okay because it has a lower amplitude. But you can then also say that, okay, goes, the reason that I wrote all these three here in pink is because it's okay, they are all just okay, going to be related. Where you mainly say power is made as going to be as okay, whereas the amount of energy that a sound wave has. Then chances you're going to, where is going to be the concentration of that energy in an area. So these two here are mainly as okay, physics, okay, we can say as okay, measurements of the amount of sound energy. Where the amplitude mainly also, well, okay, you have a lot of power, you have a great intensity, yes, okay, that's going to give you just okay, a big wave. So a big wave is going to just okay, be a big wave because it has a big amplitude. You have a lesser amount of power, you have a lesser intensity, that's going to give you a small amplitude wave. Just go to the ocean on a day where there's no wind. Or even if there's a wind, it's a slight breeze. What do you see? What do you see? You may have waves in the ocean, but those waves are small, right? So they will be low amplitude waves. Did that make sense?
Yeah.
Whereas, okay, as it's the same ocean and okay, as the hurricane season or tornado or whatever you want to call it. And what do you have then? That same ocean, yes, okay, is going to, yes, okay, be big waves. So yes, okay, that's actually physical waves that you can see. You can't see sound waves with your naked eyes, right? You may hear them as okay, big boom or as okay, low sound or something like that. Did that make sense? So yes, okay, big waves, big amplitude. Small waves, small amplitude. What gives the big waves the big amplitude? More energy. Okay. And the other way around is okay, what's going to give a small wave is okay, or what's going to produce a wave with a small amplitude is going to be as okay, lesser energy. A wave that carries lesser energy, which will be as okay a lower power or as okay a lower intensity. Did you girls get that?
Yes.
So it's okay. Willingly or unwillingly, yes, okay, we are is okay, somehow, oh shit, sorry. Somehow, yes, okay, or yes, okay, establish the yes, okay, the relationships here. The last but not the least is going to be as okay, the propagation speed. Now I already as okay told you girls as okay what propagation was. We can say it's okay, progressing ahead. Clear. So the propagation speed goes, that is mainly as okay, just going to be, we can say as okay. What is the speed at which the sound wave travels? And what we mean by speed is just going to be how fast or how slow. So yes, okay, the sound is produced by the source. But is it going to go like this? Or is it going to go like uh, 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 uh. Clear? So that's pretty much okay as what the medium will determine. And which medium was it that sound travels fastest?
Solid.
Solids. Then there will be slower in liquids and slowest in gases. And in a vacuum. Okay, girls. Okay, girls, now you may be scratching your heads and say, so what the, what's the difference between, yes, okay, an acoustic parameter and acoustic variable? Because, okay, both of them, yes, okay, are used to, yes, okay, we can say, it's okay, we can say, it's okay, describe, or be used, yes, okay, define what a sound is. Clear? But we can just use a human example and say, well, okay, let's just, okay, use acoustic variables and acoustic parameters to describe humans. Now, most likely, yes, okay, if I ask you, yes, okay, can you girls, yes, okay, to give me, yes, okay, a generalized picture of what a human looks like? Anybody? It shouldn't be that difficult. You just have to look in the mirror and say, okay, yes, what do I see? So when you look in the mirror, what do you see? And when you say, okay, what is similar between me and all other humans? And that would be Abigail who should tell me that. Okay, and Abigail is marked absent. That would be Alexander who will tell me that. I should lay down.
Can you repeat what you just said?
My question is, when you look in the mirror, what do you see? Yourself, right?
Myself, yeah.
Okay, good. Now, if you want to say, well, okay, I believe I'm a human being, and okay, as what is the similarities between me and other human beings? So how will you compare yourself to other human beings? I say, this is what we all have in common.
Everyone has skin, arms, legs. I don't know.
Hopefully also a head, right?
Yes.
So we can say as, okay, somebody standing up, have a body with 2 arms, 2 legs, and on top of that body is a head, right?
Yes.
You can say, okay, this is going to be, we can say, okay, the normal general appearance of a human being. So that will be as, okay, what we can say is, okay, the variables. Okay, so every sound wave is going to have, yes, okay, pressure, power, and it's okay. Pressure, density, and particle motion. Then we go with the parameters. Now you may look at yourself and say, well, okay, I got blonde here. Some got about black here. Some got about brown here. Right, okay, so and so. Somebody got straight here. Somebody got curly here. Okay, that will be parameters. You will say, okay, well, some people are tall, some are short. Some are thick, some are thin. Some are black, some are white, or some are of different complexions, right? Okay. So what did that do? You say, well, okay, well, he or she is a human because, okay, he or she has a head on top of the body with 2 arms and 2 legs. Why, yes, okay. I am tall. He is short. I have a straight hair. He has curly hair. And you go on. So what is it that the parameters actually do? Yes, okay, they further, yes, okay, define the characteristic of the sound.
That's for the parameter, you said?
Yes,
Okay.
just like we said, well, okay, the general thing for that accounts for all humans was body, 2 arms, 2 legs, head. That head will have 2 eyes, a mouth, and mainly as okay, nose, whereas okay, the nostrils are down here, right? Have anybody ever wondered why your nostrils are down here like this? And not up like here?
Maybe to like help you smell better? I don't know.
Okay, now you want to smell something, you just grab it. Okay, has your nostrils been up here? You may have just done it like this.
Yeah.
Okay. No idea? Just think of what it would be like if you were walking in the rain. Okay, but yes, okay, so that made us okay going to, we can say it's okay, the variables, right? Okay, we say, okay, this is mainly is okay, what a human being is okay will be looking like. But then we say, okay, well, some are short, some are tall. Okay, okay. Some maybe as okay, thin and weak. Some maybe as okay, big, bulky, and muscular. Or as okay, you're fat or obese if you want to go that way. Clear? Some may be fair, some may be dark, and some may be more of darker complexion. So on and so on. Some have straight hair, some have curly hair, some have short hair, some have long hair, so on and so on. Okay. So those that's okay, change is going to be as okay variables. No, sorry, parameters, sorry. Okay, which means is okay, further is okay, defines the sound. Okay. Any questions? So we're not going to be dealing with, okay, as the parameters, no, sorry, variables anymore, at least not. But we will have, okay, as a detailed discussion about the parameters. Your whole chapter 3 is a detailed account upon of your parameters, where we first go with definition, then the typical value with the unit, Clear? Okay, then we'll say, okay, as which component or what is going to determine this parameter here. And okay, yes, are we able to change it on our system? Can we change the period? Can we change the frequency? Can we change this? Can we change that? Okay. So those are going to be as okay, some points that we'll discuss for each parameter, and then we go on to what other parameters are related to this parameter. And if they are related, what kind of relationship do we have? Is it directly proportional? Is it inversely proportional? If it's inversely proportional, is it reciprocal or not? Yeah. Okay, goals. Now just take your lunch break, and when we come back, we may talk about it's okay what we can call in-phase waves and out-phase waves. And okay, let's come across something which we'll call interference. Okay, so should I say that I see you ladies back at no later than 12:45? Is that fair enough?
Yes.
Okay, thank you, Dan. Okay, ladies, welcome back. And any question, ladies?
No.
Okay. Now we will mainly as okay talk a bit about as okay what we can call as okay in phase, and then we will go to as okay where it means to be out phase waves. Okay, but before we do that, let us just look at a wave. Okay. Now this means okay, this is going to be what we can call as okay a baseline or a zero line. And if you look at a wave, it will go like this. Here. I mean, to understand is okay, what it means to be in phase and out phase, that means there's okay, two things that you need to clarify. And we can mean it's okay, this red top here. That's going to be as okay, what we call the peak. We can say that that's going to be as okay, the peak of the wave. Clear? And okay, and we can say this here. That's going to be as okay, we're calling the sorry. That'll be what's going to be called the trough of the wave. Okay, so we have, okay, as a peak of the wave, and we can say it's okay, this will be the trough of the wave. Is that clear? Is that clear, girls?
Yeah.
Yes.
One other thing, and that's going to yes, okay. And we can mainly say it's okay. The measurement from the peak to the baseline. That will be the amplitude. Or we can also say it's okay, the measurement from the baseline to the trough. That can also, it's okay, be considered as the amplitude. Okay. Now what we mainly had here is, yes, okay, we only have one wave. Okay. There's only going to be one wave, and okay, yes, the top is going to be the peak. The lowest point is going to be the trough. There, it says, okay, the distance from the baseline or average line to the peak, that can be considered amplitude, or the distance from the baseline or average line to the trough can be considered the amplitude of this wave here. Okay. Now, ladies, when we talk about, yes, okay, or if we say in phase. Now, first of all, right, when it says, okay, in phase is not just going to be wave, it is going to be waves. Okay, so let's just go on to another slide. And we can mainly say as, okay, now, this is still our baseline. We can say as, okay, we will have one wave, which is the red wave. So that's okay. One wave is the red wave. Clear? Now for, okay, as for waves, in phase waves, what will we need? We will need more than one wave, right? Okay. So we can mainly says, okay, now we're just going to have, okay, it's another wave. And we can make it green. So second wave is the green wave. And now girls, these two waves here is okay. The red and green wave, they are considered to be in phase. What makes them in phase waves? Mainly because, okay, when we look at it, their peaks are at the same time. And if you look at the troughs, are at the same time. Is that clear? So when two or more than two waves, It can be 3, it can be 20, it can be 15, it can be any number. But whenever it's okay, their peaks are at the same time and the troughs are at the same time, those waves are going to be considered to be in phase. Did that make sense? We can make a third wave if you want to. Even is okay, this third wave or pink wave here is okay. Okay. They are all in phase. Why? Because all these 3 waves, that's okay there. Peaks were at the same time and the troughs were at the same time. Did you girls get that?
Yes.
Yeah.
Good. Now we can mainly say, yes, okay, now then on the other side, yes, okay, what would it then mean to be out phase? And again, yes, okay, keep in mind that it's not going to be wave, but it's going to be waves. So what would I mean? Again, we will need more than one wave. Clear? We can just, okay, start with one wave and say, it's okay here. So it's okay, we had one wave, this is the red wave. Now we may have another wave. And we can say, yes, okay. Like this. Now you can mainly see that, okay, as these 2 waves here are going to be out phase. Why? Because when you look at the green and red, yes, okay, this is where you have the peak of the green, of the red. This is where you have, okay, as the peak of the green. So they happen at, okay, as different times. Likewise, the troughs. This is the trough. Oh, sorry. Oh, yeah, okay. This is the trough of the red wave. This is the trough of the green wave. So that's okay when the peaks of 2 or more than 2 waves doesn't happen at the same time, that's going to make them out phase waves. And or if their troughs doesn't happen at the same time, that's going to just, okay, make them out phase waves. Did that make sense?
Yeah.
Okay. So we mainly had, okay, as 2 kind of waves. Either waves could be in phase or they could be out phase. What make them in phase? When the peaks and troughs at this occur at the same time. Whereas, okay, when we say yes, okay, if they were out phase, if the peaks and all the troughs happens at different times. Okay. Any questions? Any questions about being in phase or out phase?
No.
Now goes what mainly as okay may happen. when we have more than or two or more than two waves traveling in a medium. They will undergo what we can call interference. So one thing that the first requirement for interference to occur is that there's going to be we can say two or more than two waves for interference to occur. If it's only one wave, if you only have one wave, there will be no interference. So we have to have at least two or more than two waves too for interference to occur. Clear? And what is it that we actually mean by interference is, let's do it this way. So first of all was that as we needed two or more than two waves. We can say we have this wave here. We can now say there's going to be another wave. Like this. Okay. Now at any specific time, these waves will come across. This is one location, this is another location, this is another location, this is another location, this is another location. What mainly happens at these locations here is that these two waves here will interfere. And what's going to happen as a result of that interference is the red wave will lose some of its identity. So will as the brown wave. Clear? And what we actually will end up with is going to be an intermediate wave. Now these two waves here were out phase. So the actual final wave that we will get is going to be the pink wave. Is going to be what we get as a result of this interference between these two out phase waves here. Okay, but interference is mainly going to be the event that happens when as two or more than two waves occur at meet or come across at specific location, and as the event that happens at that time or at that location is going to be what you will call interference, which mainly mean that they will lose their own characteristics or features. Okay. Now goes as far as interference are concerned. We will have two types of interference. Okay. There's going to be what we can call constructor interference. Other major type of interference is going to be destructive interference. Yep. Now, girls, if you just look at the word constructive, what would that mean? To build up or to add up. Whereas the destructive interference mainly is much be to break down. So just to make this okay, a long story short, constructive interference is mainly as okay going to occur if we have in phase waves. Then you will have constructive interference, where okay that means so it leads to as okay that destructive interference that's means okay going to occur when we have out phase waves. Now, what would it mean by what do you mean by constructive interference? Or how does it work? If you want to put it this way. Now, first of all, it's okay, what do we need for interference to occur? We need at least 2 or more than 2 waves. Clear? Just like, okay, as we can only say that waves are in phase if they are going to be, it's okay, 2 or more than 2 waves. Clear? Okay, so we can mainly say, okay, now, okay. Here we have a yellow wave. Yeah. There's going to be, okay, this is going to be, okay, accompanied by another wave, which is going to be, okay, let's just take the orange wave. Yeah. Okay. And we see it's okay. Okay, and what is it that we see? That, okay, yes, they are in phase. Because their peaks and troughs happen at the same time. Did that make sense, girls, so far?
Yes.
Right, okay. Now we can also say that, okay, yes, this is the amplitude and this is the amplitude of your orange wave. And we can also say that, okay, yes, this will be the amplitude of your yellow wave, or this is the amplitude of your yellow wave. But since they are in phase, and that's why I mean said that, okay, yes, we had a yellow wave and we had an orange wave. Now, what we mainly mean by as okay, constructive interference, that okay, yes, that the amplitudes here are going to be added up. And okay, yes, the final wave that we will get is going to be this wave. Okay. The remaining is going to, well, okay, probably not this big, but anyways. Let me make it a little bit more realistic. Maybe you can say it's okay, it's like, okay, as the orange wave was put on top of the yellow wave. So very you can say it's okay that the amplitude of your green wave here actually is okay, was going to be equal to the sum of the amplitude of the orange wave and the amplitude of the yellow wave. Clear? So we can mainly say it's okay that amplitude of the green wave is going to be as okay greater than the amplitude of either orange or yellow and orange wave. Or practically it's going to be as okay, the sum of the two, and that's why we call it constructive interference. Did that make sense? Yes, girls.
So just to clarify,
Mhm.
in the end phase, waves basically create a bigger wave?
Pretty much.
Okay.
The two waves will actually as okay, we can say as okay, constructively interfere to produce a final wave which is going to have a greater amplitude than either of the two waves that made it. Or three waves. You can put as many waves as long as they're in phase. They're all going to yes, okay. We can say okay, constructively interfere. Clear? And what does it mean? Yes, okay, constructively or have a constructive interference is that okay, yes, the amplitudes of the waves that are in phase mainly yes, okay, just adds up and produce a greater and greater and greater final wave. Did you get that?
Yes.
Good. Anybody else? Anybody else? Ladies,
I'm
you need to say
confused.
yes. Yes. Yeah.
So you're saying that the amplitudes added up.
Pretty much.
So for the what is it called? The peak and the trough,
Mhm.
those added up means constructive interference.
No. Listen, when the peaks are at the same time and troughs are at the same time, that makes the waves be in phase, right?
Mm-hmm.
Clear?
Yeah.
Now, when waves with an S, not wave, when waves are in phase, they are going to undergo what we call constructive interference.
Okay.
And what is that we mean by constructive interference? Is that okay, as you can mainly say as okay, the amplitudes will add up.
Okay. All right.
Okay, so you get a bigger wave. You can say as okay, small wave here, but they are in phase. They're going to add up and okay, make a bigger wave. Did that make sense?
Yes.
So if you look at the word constructive, it is pretty much okay, yes. What are you doing if you're constructing something? You're building something, you're putting things together, right? Right, dear?
Yeah.
Good. And when you put things together, you probably get something bigger out of it, right? I got 5 bricks here, 5 bricks here, I put them together, and now, okay, as I have a 10 wall or I have 10 brick wall, okay. Probably not a wall that's going to do much, but at least better than, okay, 5 bricks here and 5 bricks here, right? So I constructed something. Clear?
Yeah.
Okay, but you will only have constructed interference in case that the waves are in phase. Okay, girls? Now, on the other hand, we said, well, okay, yes, you can have destructive interference. Now, first of all, that's okay, what was it that we needed for destructive or for interference? It's the same, yes, okay, we still, yes, okay, need 2 or more than 2 waves. Clear? But when is it that we will have destructive interference? That is going to be, it's okay, where those waves are going to be out phase. What did it mean to be out phase? That when the peaks of those waves and the troughs of those waves did not happen at the same time. Did that make sense? Did that make sense, girls?
Yes.
Or we can put it this way. You may have, yes, okay, 20 drummers in a band. Or let's say it's okay, 6 drummers in a band. If they all hit the drum at the same time, that's in phase. And what do you get? The sound of all those 6 drums at the same time just makes, okay, as a loud drum sound. That is constructive interference. Did that make sense? Where, okay, as it can be the same number of drummers in a band. But when they, as okay, hit the drums at different times, they are not going to be in phase. So what is going to be as okay is going to be as okay a less louder sound. Mainly because okay, it's going to be as okay destructive interference. But let's just look at okay, yes, okay, some examples of destructive interference. Do you guys mind if I go to another slide?
No.
Good, thank you, dear. So we say as okay, destructive interference. Now, what I mainly said was, okay, yes. First of all, yes, okay, we need interference. What is the basic thing for interference? At least 2 or more than 2 waves. Clear? And what these 2 waves need to be is, they need to be as okay, oh, yes, okay, whatever amount of waves you have, they need to be out phase waves. What does it mean to be out phase? That peaks and troughs not at the same time. Clear? And if that's the case, then okay, as those waves will undergo what we call destructive interference. Yeah, I mean, he said, okay, as if constructive is adding up, then destructive is just going to be the opposite. Subtract. Now let's just take an example here. We have two, this is our baseline. And we can mainly say, okay, we have light purple wave. Clear? We have another wave. Should we take this one here? Now you can mainly say as, okay, this is the peak of the green, of the purple wave. This is the peak of the green wave. Okay, this is the trough of the purple wave. This is the trough of the green wave. So yes, okay. At any point of time, yes, okay. Okay. So these two waves here are pretty much going to be as, okay, our phase waves. What is it that they will undergo? Well, let me see. Yes, okay, this is our purple wave. And we can say, it's okay, this is going to be our green wave. And we said that it's going to be destructive. Destructive is going to be that we subtract them. So yes, okay, in this case, yes, okay, our final wave is going to be, yes, okay, something like this one here. Okay, we can use this one. This will be our final wave. Yep. Or we can even say like something like this, which may make it a little more obvious. We can say, okay, we have a small, and we may have, okay, so greater wave. So it's going to be something like this. So that will be as, okay, what we can call destructive interference. But mainly because, okay, these two waves here did not have, or were not in phase. Now we can also take another example and see that, okay, again, we have this purple wave, which may go like this. Clear? On the other hand, we may have this green wave here. It goes like this. Now we can mainly say as, okay, what do we have here? This is the peak. This is the trough. And for the green one, we can say, yes, okay, this is a trough. And we can roughly say, yes, okay, then this would be the peak. Now, as far as, okay, as the amplitude of the waves are concerned, we can mainly say that, okay, as the purple wave amplitude is going to be as, okay, greater than the amplitude of the green wave. Clear? So in this instance here, is okay, what are we still going to do what we did earlier, subtract the two. But we can mainly say, okay, our final sound is going to be yes, okay, the blue wave here is okay, that will be the final wave after, yes, okay, the destructive interference, mainly because these two waves here were our phase, but they had, yes, okay, different amplitudes. Or we can also say, yes, okay, when one had the peak, the other has a trough, and one had the peak, the other has a trough. So what do we derive from that? Okay, as in our phase interference, okay, we can say the final wave is going to be at least, or is going to be lesser than at least one of the component waves. Where in constructive interference is going to be greater than both, or the final wave is going to be greater than both of the component waves. Okay, guys. Now we may have, okay, as another example of destructive interference, which we this one here. There we say, well, okay, this is our purple wave. And this is going to be our green wave. Now we mainly see as, okay, what we just saw that, okay, as this was when the purple had its peak. And this is going to be as, okay, where it has its trough. Likewise, okay, as for the pink wave, for the green wave. It has its trough and the pink had its peak. And it has its peak when the pink or purple has its trough. But what you also may see in this instance here is, okay, I tried my best. What we can mainly say is, okay, that the amplitude of the pink wave is equal to the amplitude of the green wave. Clear? And if I say, yes, okay, I got $20, but somebody took $20. Or when we subtract two equals from one another, what do we get? Yes, okay, it may sound crazy. This will be your sound. No sound. Did you ladies get that? Have any of you ever entered a chick farm? Or seen it on the TV? Okay. Some of you will say, okay, I'm not a country girl. But what is it that you experience there? Constructive interference, right? I guess our peaks and troughs are at the same time, but on your half is destructive interference, completely no sound. Girls, this is ultrasound physics. You sound out or you signed up for ultrasound. Please make some sound. And how do you make sound? You say something. Not only if you see something. If you see something, but you still don't get it, say something. And even if you see something and you get it, say something. Okay? If not, one of these days, Dr. Brown is going to be your instructor and tell you how to, yes, okay, ask questions. Yes, Dr. Brown. How do you have the guts to ask questions?
I can't fail this class, so I have to ask questions and I have to get it.
Okay, nobody, I don't think anybody wants to fail this class. If they signed up just because they wanted to fail, then okay, yes. I don't know what to say then. Okay. My task is to ensure that, okay, yes, you don't fail. But I can only do that as long as you let me know that you got the material. Or didn't. Okay, girls? Now you guys may say, well, okay, yes, we are producing sound, but it's an ultrasound. You can't hear it. Okay. So is there anybody who has the least doubt what it means to be in phase? The least doubt of what it means to be out phase. What happens during in phase is constructive interference. And what happens during, yes, okay, being out phase is going to, be destructive interference. What happens when we, yes, okay, have constructive interference? We can mainly say that, okay, yes, it means, okay, going to add up the amplitudes of the waves to produce a final wave or a single wave with a greater amplitude than either of the component waves that were added up. Clear? Whereas the structure interference is going to be as okay be when they are out phase waves, and whereas okay they are going to be subtracted from one another. And we can say it's okay that the final wave is going to have an amplitude which is at least lesser than one of the component waves. And or if it is two waves with equal and opposite, or we can say it's okay, completely opposite waves and with equal amplitudes. There will be no sound. Because they cancel out. So it's just like, okay, as I have $20, somebody took, I used that $20. But that was being taken out of my bank account. Okay. Now, if it was two waves, it's an out phase, but it's okay, still with different amplitudes. Well, okay, I had $20, but different amplitudes, that's okay. Only $5 was taken out of my account. What is left? $15. Clear? Okay. I have a wave of $20 and somebody is okay is in phase with me and okay, it brings another $40. You put that together and what do we have now? $60. Did that make sense? I can't make it more simple than that. Okay. Any questions, girls?
No.
Good. Now the last fellow, waves of different frequencies. We will take that up tomorrow. Okay, girls? Okay, interference of waves with different frequencies. Okay, and then we have, okay, some questions to do. What day is it tomorrow?
Friday.
Friday. Ooh,
Yeah.
ooh. Okay. Good. So yes, okay. Most likely, yes, okay. We may be, yes, okay. Hopefully, be able to, yes, okay. Let's say it's okay. Start off with chapter number less. Not finish it. No. Let's go slow on that one. Okay. Clear as goals. Oh. Okay, goals. What's next? Brainstorm. What's the horizontal axis called?
X.
Huh?
X.
X. Good. Okay. What does it mean to be yes, okay, reciprocal?
It means like a fraction or a decimal and they equal up to 1 when they're added together.
Okay. Now, if I say two factors or two parameters are reciprocal to one another, what would that mean?
Doesn't like one go up by times whatever and the other one goes down by 1 over whatever the number was.
Exactly. Okay. Okay. So we can mainly say, okay, one increases 10 times, the other will increase to 1/10 of its value. Right? Okay. You can say as, okay, God forbid, but that's just an example. If you can say, okay, compare, let's, okay, you can say house pricing in two, let's say different neighborhoods. And say as, okay, the house prices are reciprocal to one another. What would that mean? That in one area, it's okay, the house prices went up, let's say 5 times. Right? Whereas in the other neighborhood, that's okay, the house prices went down to 1/5. So if that's okay, to begin with, they were both $1 million and $1 million. Where it went up to $5 million. Right, okay. Whereas, okay, as when it went down to, yes, okay, 200,000. Because that's 1/5 of $1 million, right? So yes, okay, it sucks for that neighborhood. Anyways, but that's when you can say it, right? Okay. Okay. So yes, okay. You come across that thing, yes, okay. If we get started with chapter 3 tomorrow, because we will talk about things that will become reciprocals. Okay. Okay. What does it mean to be a horizontal? Sorry, not horizontal. Sorry. What does it mean to be as okay at transverse wave?
Perpendicular and 90 degrees.
Okay. What did that mean?
The waves move up and down,
Mm-hmm.
and it moves like the waves, transverse wave moves forward, away from the media. Or media. Or the person. What?
Dr. Thomas, what?
Or the person.
Yes, Dr. Brown.
Can it be the particles move up and down while the waves move either back and forth or going to one direction?
Exactly. Okay. Okay. Or if the particles were moving back and forth, but the wave move up and down. Clear? Or if the particles move up and down, they may move back and forth. Or we're traveling in, let's say, this direction. Clear? Okay. Now, okay. Is sound a transverse wave?
No.
No, it's not. Okay, so what kind of wave is the sound wave?
Longitudinal.
Longitudinal.
Longitudinal, right? Okay. Besides being longitudinal, what other kind of wave is it going to be?
Mechanical?
Mechanical. Okay. Dr. Flores, do you want to tell us what a mechanical wave would be then? How would you explain a mechanical wave? There is some destructive interference. Okay, Dr. Ramos.
It travels by like moving particles.
Exactly. Okay, so what do you need for a mechanical wave? You need moving particles, right? Okay. Good. What's the relationship between pressure and density?
It's no relationship.
There's no relationship, right? Okay, good. Okay, it's not everything that I ask that has to be related. Okay, what's the relationship between force and pressure?
Directly.
Directly. What's the relationship between pressure and volume?
Indirectly.
No, they are not related,
No
Dr.
relation.
Nicole.
Related, yeah.
It's not volume, it's area, right? Okay. What is your unit for area?
Squared,
What is squared?
like a unit squared,
The
like
measure.
Okay, what kind of
centimeters
unit?
squared, centimeters or meters.
Exactly. So any unit of distance being squared, right? Okay, these are all, yes, okay, units of distance. Clear? Or length, if you want to put it that way, right? Okay. Right? Clear? Now, what kind of length are we talking about? Physical length that can be measured. Okay, not that you say, well, okay, I saw this movie and that was a long movie. Right, okay. That movie, that's okay. If you talk about it being a lengthy movie, that's because it was lasting for a long time. Okay, it took 3 hours and 45 minutes for you to watch that movie from beginning till the end. Yes, Shaq. They used to make movies like that. Nowadays, people don't have that much time. So that's why, okay, as a movie is over in, okay, it's 1 hour and 30 seconds or 30 minutes. Okay. Okay. So that will be as okay. What do you mean? It's okay. As okay. You say a lengthy movie, but that's okay. That's length in terms of time. You can't say, oh, that movie that was okay. That's 15 meters and 23 inches long. Okay. Okay. Good. Okay, ladies. What could be a unit for speed?
Meters per second.
Or any distance per time, right? Okay. Any unit of distance per time. Clear? Okay. Good. Capiche. Now, is frequency an acoustic variable?
No.
No. Then what is it?
A parameter.
It's a parameter. Very good. Clear? Okay. Do you guys recall what a period was?
Time that it takes the sound wave to complete.
Exactly. Time taken by one sound wave to complete. Very good, Michelle. Very good. Dr. Dixon, you okay up there?
Yes.
Okay, good. You've been quiet.
Okay, I'll be more active.
Okay. 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 What did we mean by SOK being out phase? Anybody?
It's when the peak and the trough don't line up.
Exactly. Okay. Exactly. Good. Okay, girls. So enjoy the rest of your day, unless somebody has a last word of wisdom, a punchline, any quote. A line from their favorite song to sing or so. No? Okay, girlies. Stay blessed, stay safe, breathe well, and okay, take care and see you ladies tomorrow then. Okay?
Thank you.
Thank
Okay.
you.
Bye-bye, girls.
Bye.
Bye-bye.